Look at page 152, question number 2. This is a good question, but mathematically might provide us with a little bit of difficulty. You're going to see that once we go over it, it's actually not that hard mathematically, but it's just one of those questions where you're trying to do it yourself for homework, and it's like, what do I do? What do I do? I got this variable that I'm trying to solve for in a couple different places. So question number 2 says the electric chain hoist in a garage exerts a force of 2850 up. The acceleration of the engine is 1.5 up. What's the mass of the engine? Let's draw a picture here. We don't know the mass of the engine. We do know that there is a force of the chain. What else could we call that, the force of the chain? Did anybody call it the normal force? Like usually we think of the normal force as being the force of the floor or the force of a ground pushing upwards, right? We could call the chain the normal force, right? We wanted to. I'm going to call it Fn. Yesterday, for you guys, I called it Fc. Today, I'm going to call it Fn. Hey, bottom line is, it doesn't really matter what you call it, right? As long as you recognize what it is. It's the chain pulling upwards. Its value is 2.85 times 10 to the 3 newtons upwards. We know that we have an acceleration of positive 1.50 meters per second squared. Now, technically, I don't need to label that acceleration on my free body diagram, right? But why not? Like, I might as well. I got to write down my given somehow, so I might as well put it just with my free body diagram. Now, we do have a force of gravity acting down. Does anybody want to tell me, without having been given the force of gravity, is that force of gravity bigger or smaller than the normal force? We do know here. Now, we don't know how big it is, but we know the relative value compared to the normal force here, or compared to the force of the chain. Is it bigger or smaller? I'll give you a hint. It's not the same size. It's either bigger or it's smaller than the normal force. What do you think? What do you think, Venture? Why do you think it's smaller? Good. It accelerates, not just that it's moving up. Okay? If it was moving up at a constant velocity, then you would know the normal force would be equal to the force of gravity. Right? If it's a constant velocity, the forces have to balance, right? But since it's accelerating upward, the normal force, or the whatever you're calling the upward force, has to be bigger than the downward force. So how much bigger? I don't know. I'm just going to draw it such that the force of gravity is smaller. Now, we got a problem here. We don't know what the mass is. That's what we're trying to find. But don't let that stop you from doing what you know. So often, people see a question that's just a little bit different than any other question that we've done, and they say, oh, I don't know what to do. Or, I give up. And they write down nothing. Okay, everybody in this room can write down or draw that free body diagram. Everybody can. Even if you happen to not have recognized that the force of gravity is smaller, your free body diagram will be pretty much correct. And in the end, it's drawing the force of gravity the wrong size isn't going to mess up the math in this anyways. Everybody can also do the next step. The next step is F net is equal to what? F net is equal to sum of the forces, right? We know the sum of the forces, even if we don't know what the mass is. The sum of the forces are Fn or Fc or whatever you called it, plus Fg. There we go. Everybody can do that. Everybody can do that. Even if you don't know how to solve for m here, everybody can get this far. F net is also m times a. Everybody can get this far. Even if you can't solve for the mass, that's okay. Okay, we go to sub in numbers. Everybody can sub in numbers. We don't know what mass is, but we do know what acceleration is. It's 1.5. The normal force, we know what it is. It's 2.85 times 10 to the 3, and it's upwards. And then the force of gravity is, well, what is it? M times G? M times 9.81. Now, that force of gravity is negative because it's acting downwards. I got to put a negative in for that term. I don't care whether you put that negative in front of the 9.81 or in front of the m. It doesn't matter. That term is negative. Does that make sense? Wherever that negative is, as long as it's in that term, it's fine. Right? I put it in front of the 9.81 first. I could easily do this. That would be exactly the same thing. I'm adding a negative force of gravity. Now, here's where some of you may struggle a little bit, and that's okay. We'll work through this together. But everybody should be able to get to this point. If you don't get to this point, it's because you're afraid of the question. Not because you can't do it, but because you're afraid of it. You see it's a little bit different, and you get a little scared, and you give up and you don't try. Okay? Don't be afraid to try. Okay, if you get to this point and you're struggling with solving for math, all right, I can accept that. Okay, I just can't accept not trying and not getting more or less to this point. All right, let me ask you a couple questions to help you get to the point where you can solve this mathematically, okay? Ready for this? Ready for this? Alexis, what's 1 plus 2? 3. Good. Nailed it. That's why I asked Alexis, because I knew she'd nail that. Okay. She's a smart one. All right, Ben. Oh, Ben's getting nervous now. What am I going to ask him? Ben, what's 1 apple plus 2 apples? 3 apples. Good. Okay, Ben's a smart one too. Okay. We're getting harder, right? Right, Max? Max, if 1 plus 2 is 3, and 1 apple plus 2 apples is 3 apples, what's 1m plus 2m? 3 of the m's, 3m. Good. Good, Max. All right, so if 1 plus 2 is 3, and 1 apple plus 2 apples is 3 apples, and 1m plus 2m is 3m, then what's 1.5m plus 9.81m? Do you see what I'm saying here? All I want to do is take this over to the other side by adding 1.5m plus 9.81m. It's exactly the same thing as saying 1 plus 3m, although for this one, we might actually need to pull out the calculator, right? 1.5 plus 9.81 gives us 11.31m. Do you see what I did there? Yeah, go ahead, Jack. Well, you do need the negative, but it's a negative on the right-hand side. I'm subtracting 9.81m. So how do I take a subtraction over to the right-hand side or to the left-hand side? By adding it, right? Does that make sense? If I said this was something minus 3, and I want to take the 3 over to the other side, I would add the 3, right? So I'm going to add the negative 9.81m. Does that make sense? 1m plus 2m is equal to 3m. Everybody agrees with that. So 1.5m plus 9.81m gives me 11.31m. Now I'm going to take 2.85 times 10 to the 3 and divide it by 11.31. And what do we get? 251.9, or this rounds to 3 digits, or 252 kilograms. Do you see that? How many people ended up getting that themselves? Okay, a few people. Okay, a handful of people did. How many people did get more or less to this step right here? And then kind of struggled a little bit with the math. Do you see how that math isn't really that hard? Right? We sometimes just have to put it in a context that is a little bit more real as opposed to abstract. Like sometimes in math class and it's so abstract that it's like it doesn't have any meaning to us. Sometimes we just have to put it into that meaning of apples and m's and so on. Right? Good? Okay, let's do another example question here. This one's on page 152. It says a skydiver is jumping out of an airplane. During the first few seconds of one jump, the parachute is unopened, and the magnitude of air resistance acting on the skydiver is 250. Now, this is a simplification because air resistance, unlike kinetic friction that acts just between two surfaces, air resistance actually changes. Right? If you slide something along the floor, the force of friction is the same, if it's kinetic that is, regardless of how fast the object is moving, friction will be the same. But air resistance actually increases with speed. So if you drop something, there's barely any air resistance initially, but as this thing speeds up, the force of air resistance increases, until some point when that force of air resistance actually balances out the force of gravity. What happens then? What happens when the force of air resistance balances out gravity, Luke? Yeah, you end up falling at a constant velocity. You don't speed up or slow down. We call that terminal velocity. You ever heard that term? Terminal velocity? The fastest anything can go because the force of gravity and air resistance end up balancing each other out. Now they're simplifying it a little bit here. They're saying, look, during the first few seconds, here's the magnitude of air resistance. Really it's changing, but they're assuming that it's a constant value. Which way is air resistance going to act on this skydiver as he's jumping, as he's free falling out of the airplane? Which way is air resistance going to act? It's going to act up. And we're going to say that value is 250 newtons. Are there any other forces acting here? Of course there is, right? Of course there is. Blake, what is it? Gravity, good. And is gravity going to be bigger or smaller than air resistance? Or the same? Yes. We know it's not going to be the same, because if it was the same, what would the acceleration be? Dylan? It would be constant velocity. Good. The acceleration would be 0. Because it's accelerating downward, we know the downward force, which is gravity, has to be bigger than the force of air resistance. Now, how much bigger? I don't know. Okay, we'll worry about that. We'll worry about that later on. But we know it's bigger. All right, if you got this free body diagram drawn, everybody can go to the next step. We can say, we should write down the acceleration actually. It's negative 5.96 because it's downwards. So the next step we say F net is equal to F air resistance plus force of gravity. You know what? This question is a lot like the question we just did actually. Again, we're solving for the mass, just like that last question. We're going to say F net is also equal to what? Jake? M times A, good. Now, if we were looking for the net force, we'd leave that step out, right? But looking for the acceleration or the mass, we've got to include that. Equals F air resistance plus Fg. M, we don't know what M is. A is negative 5.96. Air resistance is 250 newtons upward. Gravity is M times negative 9.81, or you could make it negative M times 9.81. Doesn't matter, as long as that term is negative. Now, I'm going to simplify this a little bit, make it look a little tidier at least. How do we take that negative 9.81 m over to the left-hand side so that we combine the like terms? Remember doing that in math class, combining like terms? I want to combine the m's. I got to take the 9.81 over to the other side. How do I do that? Yep. Yeah, it's subtract 9.81 m, so I'm going to take it over by adding. That means we've got negative 5.96 m plus 9.81 m. Gives me 3.85 m. So on the left-hand side, 3.85 m equals 250. And then we solve for m here. Solve for m, and we get, what did I do? What did I do? That's wrong. What have I done? Yeah, Ariel? Yeah, I divided 3.85 by 250. What's wrong with that? What should I have done? Yeah, Peter? Yeah, I should have divided 250 by 3.85. You know what? I don't feel like typing that in again. Let me show you a little trick here, okay? My answer is 65. 64.9. What should it be? 3 digits? Yeah. 64.9 kilograms. Anybody see what I just did there? I hadn't planned on doing that. I hadn't planned on making that mistake, but I made it, so I might as well make the best of it and show you a little shortcut. What did I do? I just took the inverse of it, right? If I went 3.85 divided by 250, and I should have went 250 divided by 3.85, then really what I needed to do is take the inverse of my answer. And there's a quick way on your calculator to take the inverse. You just take your answer, x to the minus 1, and there we go. I could have typed it out again. It just would have been a little bit more effort, and I don't know. If you could save the effort, why not? See do you see the math there? Is it making more sense now than it was, well, last night when you were working on those two questions? Yep.
How did you get the 3.85?
How did I get the 3.85? Okay, so these two terms here, I have to combine these two terms, the negative 5.96 m and the negative 9.81 m, because they're both m's. I got to get the m's together. So I got two choices. I can take the 5.96 m to the right side, or I can take the 9.81 m to the left side. Doesn't really matter, although I would suggest taking the 9.81 m to the left side, because that's going to leave us with a number on the right-hand side. So how do I take it over to the left-hand side? Well, it's subtract 9.81 m, so I'm going to take it over by adding. Negative 5.96 plus 9.81 gives me 3.85. Does that make sense? Good there? All right, I'm going to leave you with a couple more questions to work on for a few minutes on page 153. Let's draw the free body diagram for question number 1 here. It says a 55-kilogram bungee jumper fastens one end of the cord made of an elastic material. This is a good thing. Okay, you do not want to go bungee jumping with a nylon rope or a steel cable, because you probably will lose a limb or more as you jump down, and then very shortly thereafter, your life. So bungee cord made out of elastic material makes sense. Then she jumps off the bridge. As the cord is stretching, it exerts an elastic force upward on her. So if this is her, okay, there's a bungee cord attached to one ankle. I don't know why anybody would do this. Like, let's jump off. Like, the force on your knee, like when you're falling like that, and then you come to that fairly quick stop with that elastic, like the force it is to pull up with on your knee, like I feel like I would have a sore knee for the rest of my life if I did this. I will not do this ever. This is the force. We're going to say this is the force of the bungee cord. You want to call it Fn, Fb for the force of the bungee, Fc for the force of the cord, whatever. I think I'm going to call it Fn again. We do have a force of gravity acting as well. Is gravity going to be greater or less than the normal force? Greater or less? It's going to be less. It's going to be less. Okay, what's the purpose of the bungee cord? To slow you down. If it slows you down as you're moving downward, the net force has to be which way? Which force is bigger if you're moving downward but slowing down? If the downward force is bigger, you're going to speed up downward, right? If the upward force is bigger, you're going to move down and slow down. So we're going to make gravity a smaller value there. Now, we do know the value of the normal force. It's 825 newtons. We don't know gravity, but we could actually find it pretty easily by multiplying 55 times 9.81. When we do that, you're going to find that that value is less than the force of the normal force, 539.55. So sure enough, it is less, right? If it was bigger, again, the bungee cord wouldn't be doing its job. You'd be still accelerating, speeding up downwards. And you do, as you bungee jump, you do accelerate downwards for a short time, but only until the bungee cord begins to stretch. And then you start slowing down until eventually you end up stopping and then bouncing up and down. All right, now we want to find the acceleration, so we're going to say F net is equal to the sum of the forces. That's going to be Fn plus Fg. F net is also equal, Erica, F net is also equal to what? Besides F net? Yeah, good. M times A equals Fn plus Fg, and then we sub in some numbers. We know what the mass is here. 55 kilograms times A equals Fn 825 plus Fg, which is 539.55, right? Is that good? Is that good? Haley, is that good? Or am I missing anything? Or yes, good. Force of gravity is negative because it's acting downwards, right? So let's say, what do we got here? 825 minus 539, 285.45. What was that, 285.45? And then we divide that by 55. 5.19. And sure enough, that's, well, they get 5.2. We're going to round that, if we look back, we're going to round it to 2 digits because of that 55 kilogram mass there. How many people got that? Okay, good. How many people are still working on question number 2? Okay, we'll give you another couple minutes to do that, okay? All right, let's have a peek at question number 2 now. Number 2 says, during a bungee jump, the velocity of the 55 kilogram woman at the lowest point is 0 and the cord stretches to its maximum. Picture this, right? The lady is free falling. She's free falling. She's speeding up. She's accelerating. She's accelerating at 9.81 meters per second squared as she falls downward. And then the cord begins to stretch. Now, as the cord begins to stretch, she starts accelerating upward. Does that mean she goes upward? No, not at all. It just means she's moving downward and slowing down. Remember, you get a negative acceleration if you speed up in the negative direction. That means you get a positive acceleration if you slow down in the negative direction. Kind of like a double negative, right? You slow down in the downward direction, gives you a positive or an upward acceleration. Now, when we reach the bottom, when she reaches the bottom, she stops. Let's look at question A, the direction of her acceleration at the lowest point of the jump with where she is accelerating due to gravity. When she's accelerating just due to gravity, her acceleration is downward and it's negative 9.81 meters per second squared. When she's at the lowest part of the jump, the lowest part, she stops. Which way is her acceleration? Is it 0? No. Her velocity is 0. Remember that acceleration is not related to velocity. Acceleration is related to what? It's almost velocity, but acceleration is related to the change in velocity. Even when she stopped, her velocity is changing because a half a second later she's going to be moving upwards, right? Now, which way is the bungee cord pulling on her when she's at the lowest point? Upwards. That means when she's at her lowest point, the acceleration will be, if the net force is upwards, the acceleration will be upwards. She's at her lowest point, the acceleration will be upwards. Does that make sense? You can be moving downward. Isn't question B kind of redundant there? Yeah, we just answered it, right? You can be moving downward and have an upward acceleration. Now, when she's free falling, when she's accelerating just due to gravity, her acceleration would be downward. But as she's slowing down because of the cord, her acceleration would end up being upwards. But as she comes to a complete stop, her acceleration is upwards as well. Just because she's moving downward or stopped doesn't mean she doesn't have an upward acceleration. Remember that it's related to the change in velocity, and the change in velocity is a positive value. Think about that. Okay, when she stops at the bottom, her final velocity is 0. 2 seconds before that, her initial velocity might have been -6. 0 minus -6 is +6. So as she moves downward and then stops, her change in velocity is still a positive value, meaning her acceleration is still a positive value or an upward value. All right, let's try another one. Ooh, this one looks kind of... Actually, let's not do this one. Let's go straight to the harder one on page 156, 3.11. It says a 20 kilogram truck tire, let's label that right here. Everything else seems to be labeled on the diagram. Is lying on a horizontal frictionless surface. Now, if there was friction, that would make things a little bit nastier, but we could still do it. The tire is attached to two light ropes that pass over a light frictionless pulleys to hanging pails B and C. B has a mass of 8 kilograms. C has a mass of 6 kilograms. And we want to find the acceleration of this system. Whoa, this looks awful. I see a couple people doing this. No, that don't. I can see their head nodding like that. That doesn't look awful, they're saying. In fact, it isn't actually that bad. It looks kind of ugly right now, but once we see this done, it's kind of like, oh yeah, it's just like we just did. Like it's like we just have been doing for the last few days here. All right, let's label the forces acting on this thing, okay? We've got masses, but we don't have a free body diagram drawn yet. Let's draw the free body diagram. Are there any forces that act on this tire? Does gravity act on the tire? Sure it does. Does the normal force act on the tire? Yeah, they cancel, right? They cancel. Yep.
There's a force from both the pails, but the pail B force is bigger.
Okay, so there's a force acting on both of the pails, but the force on pail B is bigger. How come? Okay, so what is it that causes that force on pail B and pail C? Gravity, right? Gravity pulls down on pail B. I'm going to call this FB, but really it's a force of gravity on B, right? And I'm going to call this one FC. And Ariel said that FC is smaller than FB because the force of gravity will be smaller on a 6 than it will be on an 8. Right? Now, listen, these ropes in here are applying forces as well. But listen carefully to what I'm about to say. Those are what we call internal forces. If I was analyzing a problem where you pull the box, like we did on our quiz, where you pull the box one way and I pull the box the other way, we'd pay attention to the force that you pulled with and I pulled with, right? We wouldn't pay any attention to the molecular forces that were acting between the atoms of the box, right? We wouldn't pay any attention to the internal forces. When we're solving that treasure box problem on our quiz, we just paid attention to the external forces, the force that you pulled with, the force that I pulled with, not the molecular forces inside, not the internal forces. So we're not going to pay any attention to the internal forces here either. The ropes that connect, we'll say atom 1 to atom 2 to atom 3, or pail to tire to pail. Those don't matter to us. It's the only thing that affects the motion of this system of pail, pail, and tire are the external forces. Okay? All right, now what we want to do is simplify this a little bit here. Actually, before we do that, let's get a value for FB. What do you think that value for FB is going to be? Somebody said, Ariel said that it was due to gravity, right? So what do you think that force FB is going to be? Good. 8 times 9.81, m times g, but not like 34, all the masses combined. It's just, look, there's a force of gravity pulling on the 8 kilogram mass. So it's 8 times 9.81. And when I multiply 8 times 9.81, I end up getting a value of 78.48. So let's fill that in here. And FC is going to be what? 6 times 9.81 then, by that logic? Which is, I think it's 58.86 newtons. Now, watch what I'm going to do here to simplify this a little bit. Actually, you know what? No, I'm not going to do that yet. Don't write anything down yet beyond what you see on the board right now. Okay, what I'm about to show you, I don't want you to write down quite yet. Next step would be to say F net is equal to the sum of the forces, right? That is the sum of the external forces here. We have FB plus FC. Anything else? Nope. There's ropes, but those are internal forces. That's the ice cream banging against the side of the truck, right? Which doesn't really affect the motion of the truck. Internal forces. We don't care about that. Now, M times A is equal to FB plus FC. And then we say what? M is, interesting here, M. I got 3 of them. What do I use? 8, 26, what? Yeah. 20? Yeah, it seems like it might be the 20, doesn't it? It's not right, though. Yeah. Yeah, we got to use all of them. Got to use all of them. It's 34 kilograms. Look, the whole thing is being accelerated, right? Like, if I want to find the acceleration of the ice cream truck, I got to include the mass of the truck and the ice cream inside, right? Even though those internal forces of the ice cream banging up against the wall don't matter, the mass of the ice cream matters. So I got to include that here. And what's FB? 78.48. And what's FC? 58.86. Should I put any negatives in here? They're both downward, aren't they? Do I make them both negative? Downward force, 78. Downward force, 58. Does that make sense? Remember I told you not to write that down yet? I told you that because that's not quite right. Most of it is, actually. So if you wrote it down, it's not like you wasted your time. But let me redraw this. Let's pretend that pail B is kind of on the same plane as the tire. So we stretch it up like this, and we stretch pail C up like this. And then it starts looking like this. This is B, this is the tire, A, and this is pail C. And we've got a force over here of 78. And we've got a force over here, FC, of 58.86. What do you think now about these? Does that make sense what I've just done there? Like, that's kind of the same, right? FB and FC are opposing each other, even though they're both pulling down. I'm pretending one's to the left and one's to the right. Now I want to make FB negative, but I want to make FC positive. Despite the fact that it's acting down, I want to make it positive here. So I tend to redraw it like this because it illustrates 2 points. One, it reminds us that even though the forces are both down, they're opposing each other, and one has to be positive. And secondly, it kind of helps us to understand that really I can treat this as one object that has a mass of 34 kilograms. And that's why I sub in 34 kilograms right there. Now, let's just finish this up here. Okay, let's just quickly finish this up before you take off here. We're going to say, hold on, please. We're going to say negative 78 plus 58.86. We're going to divide that by 34. And we get an acceleration here of negative 0.577 or negative 0.58 meters per second squared. Here's your homework for tonight. Page 157, questions 1 and 2.